In this video recording, we will take a look at the following example. Determine and classify the critical points of the function f of xy equals y squared minus 4y cosine x. Our first step here is to find the critical points of this function. And just like for functions of one variable, critical points are points where the first derivatives, partial derivatives of this function are equal to 0 or undefined. And so we begin by looking at our function and computing first order partial derivatives of this function. Well, let's compute the partial derivative with respect to x. When we compute the first derivative with respect to x, we are thinking of y as a constant. And in particular, then y squared is also a constant. The derivative of cosine x is negative sine x. So putting all of this together, we find that the partial derivative of f with respect to x equals 4y sine x. Similarly, we can find the first order partial derivative with respect to y. This time we are thinking of x as a constant and y as the variable that it varies, and differentiate. The derivative of y squared term is 2y. The derivative of y equals to 1, and then negative 4 and cosine x are constants, so we find that this derivative equals to 2y minus 4 cosine x. These derivatives are defined for all values of x and y, and to find the critical points, we set both of these derivatives equal to 0. We get a system of two equations with two unknowns, x and y, and our next goal is to solve for x and y. We look at the first equation, and it says that the product of 4y and sine x must equal to 0. When a product of several numbers equals to 0, at least one of them must be 0. 4, of course, is not 0, so the possibilities are either y equals to 0 or sine x equals to 0. And accordingly, we consider two cases. Case 1, y equals to 0. Then we can plug that into the second equation, plugging in y equals to 0. We then find that cosine x must equal to 0. And then we solve for x. One way to do that is to look at the unit circle. And on the unit circle, we look for points that have 0 x coordinate. A little confusing notation here, because cosine x, x here refers to several different things, x and y coordinates in the coordinate system, and also x being the distance around the unit circle from the point 1, 0 to the point on the unit circle. So just keep that in mind, and don't confuse the two, even though they're denoted here by the same letter. And okay, and so we get these 2 points on the unit circle. The first point corresponds to values of x equal to pi over 2 plus a multiple of 2 pi, which we can write 2 pi k, where k is an integer. And then the other point corresponds to x values negative pi over 2 plus, again, a multiple of 2 pi. And so this is our first series of critical points, where x coordinate equals plus or minus pi over 2 plus 2 pi k, and then the second coordinate is 0. And now we go to the second case, returning back to our first equation. Remember, the first case, for that derivative f sub x to equal to 0, either y must be 0 or sine x must equal to 0. And so we now come to the second case, where we assume that y is not equal to 0. then we conclude that sine x must equal to 0. If sine x equals 0, then of course cosine x is either positive or negative 1. And if we plug in, if we solve for y, the second equation, then we find that y equals to 2 cosine x. And depending on whether cosine x is positive or negative 1, we obtain that y equals to positive or negative 2. Now, solving for x, cosine x equals plus or minus 1. Again, we can solve this equation using the unit circle. On the unit circle, we this time look at points that have x coordinate equal to positive or negative 1. The first point is corresponds to x values which are multiple of 2 pi. Integer multiple of 2 pi, and then the second point corresponds to values of x which are pi plus an integer multiple of 2 pi, and this gives us the critical points 2 pi k comma 2 or pi plus 2 pi k comma negative 2. We found all critical points of this function, and next we go to the second step, which is to classify the critical points. This simply means for each critical point we need to determine whether that point is a local maximum, local minimum, or a saddle point. And for this we use the second derivative test. Again, it's sort of similar to how we do this for functions of one variable, except that the second derivative test is more complicated in this case. First, we need to compute the second order partial derivatives of our function, returning back to our first order partial derivatives. Here they are. And now second order partial derivative of f with respect to x both times is going to be 4y cosine x. We're differentiating the first derivative of f with respect to x, again with respect to x, thinking of y as a constant, and so that gives us 4y cosine x. Differentiating f sub x with respect to y, thinking of x as a constant, we find that the mixed partial derivative of f with respect to x and then with respect to y is 4 sine x. And then differentiating f sub y, with respect to y, we simply get 2. So it's a constant derivative. And now we return to our critical points. Remember, we had two cases. The first case was y equals to 0, cosine x equals to 0, and sine x values either positive or negative 1. We plug these values into the second order derivative that we just found, and we find that fxx, second order derivative of f with respect to x both times, is equal to 0. The mixed partial derivative for sine x is going to be either positive or negative 4, and then fyy is 2. And based on these numbers, we then compute the number called d. D stands for the discriminant. And that number is computed by multiplying fxx and fyy and then subtracting the square of the mixed partial derivative. And we get 0 times 2 minus positive or negative 4 squared. This gives us negative 16. And we find that for these critical points, the discriminant is negative, and the second derivative test tells us that this means that these points are saddle points. In the second case, sine x is equal to 0. Y value is going to be plus or minus 2, depending on whether cosine x is positive or negative 1. And so when we compute the second order derivative of f with respect to x both times, we get 4 times plus or minus 2 times plus or minus 1. Here it's important to see that the way the signs plus or minus correspond to each other. And so, for example, if the value of y is equal to positive 2, so if we're using the positive sign, which is on top here, then the corresponding sign for cosine x is also positive right here. And so we get plus 2 times plus 1 times 4, which is positive 8. Now, if the value of y is negative 2, if we choose the negative value, then that happens when the value of cosine x is negative as well. So minus goes with a minus, plus goes with a plus. And in both of these situations, the value of f(x)(x), the second derivative of f with respect to x, comes out to be positive 8. The mixed partial derivative, which is 4 times sine x, will come out to be equal to 0. Fyy is equal to 2. We compute the discriminant. 8 times 2 minus 0 squared. This is 16. This is positive. And also, let's note that the second order partial derivative of f with respect to x both times is also positive. f(x)(x) is equal to 8, positive. And in this case, the second derivative tells us that these points are local minima. And so, to summarize, we determined that this function has saddle points, and it also has local minima. It does not have local maxima.